Hello, in the following video, we will be taking a look at how to analyze both stress and strain transformations. In order to start off with this, let's take a look at what should be a fairly simple example by now. Let's take a look at just a standard beam that is being placed in compression due to an applied force on either end. By now we know that as long as we know the externally applied loads, we can then place an imaginary cut at any location we desire along the beam. And on the face of that cut, we can examine the internal reaction forces that are required to keep the beam itself in static equilibrium. When we analyze the forces along plane AA, we actually get a fairly simple breakdown. And by looking at the sum of the forces in both the x and y direction, we can determine the value of both the internal normal force and shear force, forces which will result in the creation of normal stresses and shear stresses. In this case, we get almost the trivial solution that the normal force is equal to the magnitude of the applied force, and that the shear force on this plane is actually 0. And while that situation is actually fairly straightforward, what happens if we place plane BB on the face of this beam? This cut is no longer perpendicular to the applied forces, and instead is at an angle between the x and y axes. If we then analyze the forces on the face of this cut, we will see that in order for this beam to remain in static equilibrium, the force in the x direction is actually resisted in part by both the normal and shear force. And this results in the creation of a normal force that is equal to the applied load F times the cosine of theta, the angle that the plane was placed at, and that the shear force is equal to F times the sine of theta. Now a few of you may be scratching your heads right now, because it seems like we may have just discovered that the forces inside of a material are dependent on how we, the viewer, actually look at them. However, that's actually not the case, and in order to figure out why, we're actually going to take a closer look at this type of a problem. Inside any material that is subject to plane stress, or stress that is just within one plane, we can analyze a differential volume element and look at the stress on this element. Typically, we break this stress down into a conventional Cartesian coordinate system in the x and y directions. However, sometimes it's actually convenient to take a look at stresses in a rotated frame of reference. In this example, we can rotate our differential volume element and angle theta in the counterclockwise direction. This will result in an element that is rotated and that now has stress elements sigma x prime, sigma y prime, and tau xy prime, indicating normal and shear stresses in our new coordinate system. Once in the rotated position, the magnitude of the new stress values can be calculated using the stress transformation equations. As you can see, the stress in the x prime direction is actually a function of the initial stress in the x and y directions, as well as the shear stress on the x plane in the y direction. And importantly, if the element itself is rotated an angle theta from its initial orientation, the stress transformation equations actually depend upon twice that angle. Don't forget that as we move forward. In order to get a better look at how these equations actually predict stresses to transform, let's take a look at an example. So on this volume element, you can see that we have a positive normal stress in the x direction of 20 megapascals, a negative compressive stress in the y direction of negative 10 megapascals, and we have a negative shear stress of negative 20 megapascals. In order to examine the state of stress predicted by these stress transformation equations, let's plot the rotated shear stress versus the rotated normal stress. Note that on this coordinate system I've drawn shear stress as being positive pointing down, while positive normal stress points to the right. With that said, I can plot my initial starting point at the location shown on this chart. Once we have the initial state of stress, we can plot sigma x prime and tau xy prime for various different angles of theta. In the following example, I've plotted 7 new data points, incrementing 11.25 degrees between each data point. As you can see, when we plot a sufficient number of points, a familiar shape begins to take form. If we were to plot at infinitely many data points, we would actually see that we form a circle that represents the state of stress given by the initial problem. This is referred to as Mohr's circle. So what this lesson actually teaches us is that any data point that falls on Mohr's circle actually represents the same exact state of stress as any other point on that circle. The only thing that changes is the coordinate system in which you view that state of stress. Now, an important point to remember when constructing and analyzing Mohr's circle is to always remember the orientation of the coordinate system, namely being positive normal stress is to the right and positive shear stress is actually plotted down. Once this is done, the angle theta is positive in the counterclockwise direction. Furthermore, it's important to realize that when you rotate an object theta degrees in a physical sense, you actually need to rotate it 2 theta degrees on Mohr's circle in order to calculate the new state of stress. The study of transformations has actually become particularly useful for studying strain transformations on the surface of different materials. In order to see how we convert from our stress transformations to strain transformations, first recall Hooke's law. Hooke's law says that stress is proportional to the modulus of elasticity in that direction times the strain in that direction, and in this case you can see I'm indicating the x direction. However, if we have an isotropic material, that means that the modulus of elasticity is independent of direction, and therefore the modulus in the x and y directions will be equal to each other. If we utilize Hooke's law and plug these values into our stress transformation equations, we will find out that the modulus of elasticity cancels out and we end up left with the strain transformation equations. You can see they are nearly identical to the stress transformation equations, however they replace the strain values for the stress values. As mentioned, these equations come in quite handy when analyzing surface strains utilizing strain gauge rosettes. Strain gauge rosettes are typically comprised of 3 or more different strain sensors that are rotated at various different angles, on this picture indicated as theta A, theta B, and theta C. By knowing the angle between each of the different strain gauge rosettes from the principal x-axis, as well as the strain measured in each of these rosettes, we can utilize the first strain transformation equation to determine the state of strain and therefore the state of stress at the location that the strain gauge is mounted. So as mentioned, by recording the state of strain in sensors A, B, and C, and also knowing the angle of rotations theta A, theta B, and theta C, we obtain 3 simultaneous equations. And by solving them, we can determine the values of strain in the x direction, strain in the y direction, and shear strain on the x-plane in the y direction.